Hey, we are going to talk about the physics of objects that are rolling. And we're talking about a particular kind of rolling, or at least clarification, that we're talking about rolling without slipping. Slipping. So, I thought I would just do a little demonstration. You know, if we were really here in class when we had little bits of notes to do, would usually have some kind of gear out, some things, physics stuff, to demonstrate whatever it is we're talking about. So, if we were talking about rolling in class here, this ruler is propped up at one end just by a pencil, so not very much. If we measured the angle of that, it's just, I don't know, a few degrees of elevation. But it's enough for if I release this, it goes on rolling down that little ramp that I made. It's not steep enough for it to slip. So the first thing that we need to understand is something that I think is just a little bit counterintuitive. How is it possible for this to roll without slipping? Now let's just imagine for a wee second that this ramp is made of ice or some other completely frictionless surface. If there was no friction at all and we put this at the top of the ramp, what would happen? Well, it would be like any other frictionless thing. We've done that problem a few times. It would just slide down the ramp like this because there's no friction. So what we need to understand now and realize is that it is in fact friction that allows things to do this thing that we call rolling. If there was no friction, it wouldn't roll. It would just sort of like slip or slide or slide down the ramp without rotating. But in fact, it's the friction that is causing it to rotate. Now, it's possible for things to kind of like roll and slip at the same time, and that is a messy problem. Anytime there's kinetic friction involved, things are it's kind of messy to deal with in the so-called real world. But it is possible that something kind of like my little ramp I just had set up there for you, that something could roll without slipping. And I need you to understand here, this is the counterintuitive thing, that look at the contact point, if you can kind of focus right there on where the round object is contacting the ramp. There is, that contact point is not moving. It's not doing this kind of friction, like it's not doing kinetic friction. The point of contact between the disk and the ruler is remaining, although it's the contact point, like what part of the disk is touching the ruler is not changing. The contact point is not shifting. So this is not kinetic friction. It's actually static friction because the part of the object that's touching the ramp is not changing. So this is static friction. It's not like, not kinetic friction. Static friction. Not kinetic. Static. So that's a little counterintuitive, I think. And then, like, when does rolling and slipping happen? Well, that's when there's not enough static friction, like just like in a regular old static friction problem. Okay, so that is an important thing to understand. Now, what I'm going to try to do for you here is just based on what we know from, let's see, forces, torques, kinematics equations, and energy considerations, I'm going to derive for you some stuff about rolling. And I'm going to do it in two different ways. We'll talk about what you need to know and all that. All right, so let's say I have an object. I wouldn't make this picture too small now. And it's rolling down a ramp. Let's say that's at angle theta. And here is my object. It's going to roll down this ramp. And let's say it has a rotational inertia I, whatever that happens to be. Maybe if it's a disk, then it would be like 1/2 mr squared. If it was a solid ball, then it would be like 2/5 mr squared. If it was a hollow ball, then it would be 2/3 mr squared, and so on and so on. But whatever it is, I'm not going to pin it down here. It's just has rotational inertia I, and it has a mass of m, whatever it is, and let's say it also has a radius of r. So there's some things about that. So let's see. Let's make a force diagram here. Now, when you have something that's rolling down a ramp, when you have something that could possibly have torques acting on it, where you put the force matters. So I'm not going to, like we used to do in the olden days, and we still do sometimes now, I'm not going to reduce this down to a dot and then pin all the forces on that, because it matters where the forces go, whether they're causing a torque or not. So first thing I would do would be to pin the gravitational force onto this. Where's the gravitational force? Where's the right place to put that? Well, gravitational force gets pinned to the center of mass of an object. So that would be here. And that would be equal to mg, of course. And how about the support force? Well, there's a support force, and that is going to, we're going to draw that coming right from that contact point, because that's where the support comes from. And it would be perpendicular, of course, like this, the force normale. And then what about the friction force? Of course, if we're talking about rolling without slipping, there has to be a static friction force. And where would it be? It would be at the point of contact. Which direction? Would it be going this way, or would it be going this way? Well, this object is going from not rotating to rotating in this direction. So there must be a torque causing that to happen. So this friction has to be up the ramp. Like this. I hope you can see that okay. That's a little arrow right there. And that is my static friction right there. Those are the forces, and that is the force diagram. So, well, we could break up. I'm going to do this in pencil. Well, let me just talk about this. If I were to draw in the components of the gravitational force here, I would draw them in. Here's the cosine component. Here's the sine. So this would be mg cosine theta, which would be equal to the normal force per usual. And then this would be mg sine theta down the ramp. So what I'm going to do now is I'm going to do Newton's second law in its translational form. Translational meaning that we're talking about moving from one place to another. And then over here, I'm going to do Newton's second law in its rotational form. And I promise I'll move the paper over in case you can't see that whole thing. So Newton's second law in translational form, sum of all forces is equal to mass times acceleration. So let's look at the diagram here and see if we can figure out what is the sum of all forces. So the normal force and the cosine component of the gravitational force, they're going to cancel each other out like they always do. There's no motion in this direction. In this direction, we have the sine component of the gravitational force, so mg sine theta, down the ramp right here. And then we have the friction force opposing that. That's right here, minus the static frictional force. And not really anything else I can do there. That's it. For now, at least. And now how about the rotational form of Newton's second law? Sorry, slide, there we go. So sum of all torques is equal to I alpha. That's the rotational form of Newton's second law. So back to our force diagram here. Which of these forces is causing torque? So torque is equal to force times radius times the sine of the angle between those things. So here we have the gravitational force acts right on the center of the object. Does that cause it to rotate? No. And if that should be clear, like if I just dropped this object and it wasn't like already rotating, then it would just fall like this. The gravitational force on it does not cause it to rotate. Okay, so no torque from that. How about the normal force? Well, that doesn't cause any torque either. If you push directly up on something, right directly in line with through its center like that, then the force times the radius, the force is not zero, the radius is not zero, but the sine of the angle between them, the angle between those is, it's actually 180, 0 or 180 depending on how you want to look at it, and the sine of 0 or 180 is 0. So that's how our mathematical model for torque takes care of that. And you can see if you push right on the edge there, on that line through the middle, that doesn't cause it to rotate, no torque there. But this, the static frictional force along the bottom there, that is going to cause it to rotate. So it's only this that causes the rotation. So torque is force times radius, and that's equal to I alpha. And anticipating that I'm going to try to combine these equations, alpha is equal to A over R. Right? Right. So, okay. So what am I going to do here? Well, I don't know what this frictional force is, and it would be nice, like, if we could get to the point where we had the acceleration, and we could say, okay, this is what the acceleration of this rolling object is. That would be good. So let's go ahead and try to get there. So static friction is equal to I over R squared times acceleration. In different ways you could write that, but I'm going to package it like that. I'm just dividing that R over there. Okay, so let's plug that in over here. So I've got mg sine theta minus the frictional force, which is I over R squared times A is equal to mass times acceleration. And I'm trying to solve for acceleration. So I'm going to do two moves at the same time here, two algebra moves. I think you can handle this. Might want to put your seatbelt on. So I'm going to divide all the terms through here, divide the entire equation through by m, and I'm going to add this to the other side over here. And I'm going to, no, I won't do more than that. Okay, we don't need to do 3 algebra steps. There's no reason to do that. Okay, so that is going to leave g sine theta. Remember, I'm dividing through by m, and then I'm going to add this to the other side. So when I have this on the other side here, there's my acceleration. Remember, I divided through by m. Then it's going to be plus, and I'm going to have I over m r squared, right? Because I'm dividing all 3 terms. These two actually had an m to divide out. This one didn't, so I end up with an m on the bottom, times a. And then the other thing I was going to do, you probably could have handled it just fine. I'm going to factor out the a here, and that would leave me like a 1 1 plus this. And so now I'm going to do two moves again. I'm going to factor that a out. That would leave me a times quantity 1 plus I over mr squared. So there it is. That's the acceleration of a rolling object. That's not on your equation sheet. Do you know what it means when there's an equation that we know that is not on the equation sheet? It means that in a free response question, you cannot just drop this onto the reader, whether that's me or the College Board. So if this comes up, and this is something that does come up frequently in free response questions, you need to be able to do this. You need to be able to derive this. That's not always true. Like when we derived, for example, like what's kinetic energy? It's 1/2 mv squared. We did a little bit of a derivation of that. You don't need to know how to do that, but you do need to know how to do this. So that is important. And that's why in your lab, I'm asking you to include a version of this derivation in that document that you submit to me. Okay, so there it is. Now let's just kind of snoop around this a little bit. If you have an object like a dry ice puck, for example, that's going down a ramp, what's the acceleration of the dry ice puck down the ramp? Well, it's just mg. It's just g sine theta, right? Because that's the part of the gravitational force that's down the ramp. The m's divide out. Ma equals mg sine theta. So acceleration is just equal to g sine theta. And you can see that that is showing up here. Now, what's the rotational inertia of a dry ice puck that's not rotating? Well, it doesn't really have any rotational inertia, right? So it's kind of like that's 0. So, of course, if that was 0, if you don't have any rotation, then you just get the g sine theta. Now, what if we do have a rotating object? Well, the I is going to be something like 1/2 mr squared, or maybe like mr squared if it's a hoop, or 2/5 mr squared if it's a solid ball, or whatever. But that's the form of this, of an I, is some coefficient times mr squared. So what happens if you have I over mr squared? Well, the mr squared part gets divided off, and you just get the coefficient here. So this number, what we're seeing here is the acceleration of an object rolling down a ramp is the g sine theta that we would expect, divided by 1 plus whatever the coefficient is on its rotational inertia. And that can't be, for a rolling object, this cannot be bigger than mr squared, right? So the slowest object, or the object with the least acceleration, would be a hoop, where all of the mass is at the outside. That's going to cause it to accelerate the most slowly. So there you go. And of the objects that we are going to encounter, the typical kind of objects, the one with the smallest rotational inertia would be a solid ball, right? Which has, that's 2/5 mr squared, and 2/5 is 0.4. So you think about that, and how you could use that. Now, there's another way to derive that, and I'm going to do that for you now. So this is the energy approach. Sorry, I can spell. Oh, it has 2 P's, doesn't it? Approach? Oh, who cares? That may be 1 or 2 P's, depending on how the word approach is spelled. Yep. Okay, this is the energy approach. So let's say we have an object here. It's the same object. It's got a rotational inertia of I. It's got a mass m, and it's got a radius r. And we're going to let it go down this ramp, and the length of this ramp is L, which means that this height right here is L sine theta. Right? And that's the distance that it's going to go from here to here is L. Okay, so what happens energy-wise here? There's no non-conservative forces. There is static friction, but that is, it's not doing any work because that friction force is not actually moving the object. It's not static. It's not kinetic friction. So that is not actually changing the energy situation. So we can take a conservation of mechanical energy approach to this. At the top of the ramp, we have gravitational potential energy. This is what we would call the conservation of energy equation that I'm writing here. And when it gets to the bottom of the ramp, it's going to have kinetic energy, but it's going to have both translational kinetic energy and rotational kinetic energy, because it's going to be moving down the ramp like from here to here, but it's also going to be rotating as it does that. So it has both of these. Okay, so let's see. mgh is equal to, translational is 1/2 mv squared, rotational is 1/2 I omega squared. Now let's plug in let's see what we can do here. The h is L sine theta. One half mv squared. Not really anything I can do there. I can try to get this into, well, I can do this at least. 1/2 I. The omega is v over r. That is only true. I should have said this for the last page too. I can only make this substitution here because there's no slipping. If there is slipping, then that's a bust. This depends on the outside of the disk moving at the same speed as the center of mass, right? And of course, if you're not slipping, the outside of this is going to be moving just exactly the same as the center of mass. If there's any slipping, whether it's rolling like slipping forward, slipping backwards, whatever, then you can't do that. Okay, so what do we do here? How about if we multiply through everything by 2? I think my goal here is all these things are constants. This should be a capital R. That's what I use here. All these things are constants except for this v. I don't think I know what that is. So I think my goal here will be to try to solve for that v. So I'm going to multiply by 2 and divide by m. Can I do those two things at the same time? I'm asking your permission. May I? So let's see. Multiplying through by 2 because I want to get rid of those fractions, and dividing by m. So multiplying this term by 2 and dividing by m. So that gives me 2gl sine theta. Multiply by 2, divide by m, so that's just v squared. Multiply by 2, divide by m. So that gives me, there's my I over mr squared showing up again, times v squared. Okay? And then kind of like we did in the last one, I'm going to go ahead and factor out the v squared and divide that out over here. So v squared would be equal to this, 2gl sine theta, divided by 1 plus I over mr squared. And that's what v squared would be equal to, so v is equal to that. Yikes! That's crazy. What are you going to do with that? Well, I wouldn't say you would want to memorize that. That's something that you would want to be able to derive. And in lots of problems, you would actually have an I here, so it doesn't come out to be quite as messy as that. Although, I don't know, maybe that's not messy. The 2GL, just to understand here, in our regular old energy type problem, just a little scratch work, when you have gravitational potential energies turning into kinetic energy, and you have something that drops some height h, then mgh is equal to 1/2 mv squared. The m's cancel, so v is equal to the square root of 2gh. We've seen that happen lots and lots of times, square root of 2gh, right? So the square root of 2g, the L sine theta is the h here, right? So that expression, square root of 2gh, that is happening. And notice that similar to here, the factor that we're dividing by this factor, of course, here it's a square root, so it shouldn't be too surprising that it came out to look like that. And maybe if we look at it in that way, it is kind of nice. Nice. So what are you going to do with that? I mean, I'd like to be able to reconcile this approach here with this one. So from here, since it still has a constant acceleration for sure, constant acceleration, I mean, we know what it is from the last page. So constant acceleration means I can use kinematics equations, including the one that has v final squared equals v initial squared plus 2a delta x. And let's see if we can apply that to this situation. What's my VF squared? It's this here. So, right, that's the velocity at the bottom of the ramp. So, squaring that would give me 2GL sine theta over 1 plus I over mr squared equals, initial velocity is 0, 2 times acceleration times delta x, the distance that it goes through, that's just L. Right? So it looks like on both sides of this I have a 2 and an L. So that cancels with that. And the L cancels with that, and I get acceleration is equal to g sine theta over 1 plus I over mr squared. Boom, there it is. So of course it is, right? I mean, we had to get the same thing doing it both ways, otherwise our physics would be somehow broken. So check. That's it. So this is the energy approach. You can, in problems where you're interested in acceleration and velocity of objects rolling down ramps, usually if you're interested in the velocity, you take this approach. If you're interested in the acceleration, you take this approach. But once you have one or the other, you would never do this to find the velocity and then go through all of this to find the acceleration. That's crazy. Once you have one or the other, like if you found the velocity first, then use kinematics to get the acceleration. If you found the acceleration first, then you could have used, like we could have used kinematics to find this velocity to get this expression. But I wanted to show you how to get it using energy considerations. That is it, and I need to stop talking because if I go much longer, I'm going to owe you another free pizza. So that's it. Bye-bye.